All right, buckle up, everybody, because today we are diving into the nature of light.
Ooh, that's a big one.
It is, and you know what got me thinking about all this?
What's that?
This YouTube video you sent me.
Oh, yeah.
Yan serio que la luz from QuantumFracture.
That's a good one.
It really is, and it's got me thinking about, how much we take light for granted.
Yeah, you don't really think about it until you start digging deeper.
Exactly, and that's what we're doing today. So
Let's dig.
let's dig in. I mean, where do you even begin with something so fundamental?
Well, the video starts off with Newton
Right.
and his idea that light is made of these tiny particles.
Like little bullets of light.
Exactly.
Yeah.
And that actually explained a lot of things at the time.
Like what?
Like how prisms split white light into all those colors.
Yeah, I remember learning about that in school.
Right. It's like each color is a different kind of particle.
With like a different mass or something?
Exactly. It's a really neat visual.
It is, but then the video mentions some experiments that kind of messed with that whole idea.
Yeah, there were a few things Newton's particle theory couldn't explain.
Like what?
Well, imagine shining light through a tiny hole.
Okay.
If light was just particles, you'd think a smaller hole would make a smaller spot of light,
Yeah.
right?
Yeah, that makes sense.
But that's not what happens.
Really?
Nope. As you shrink the hole, the light actually spreads out even more.
Huh. So it's like it's waving around or something.
That's exactly what it looks like, a wave.
But waves usually travel through something, right?
You're thinking of like sound waves traveling through the air.
Yeah, exactly.
Well, back then, they thought there might be some invisible stuff called luminiferous ether that light waves traveled through.
Luminiferous ether.
Yeah, it sounds fancy, right?
Very fancy.
But eventually, scientists figured out that ether didn't actually exist.
So no ether, but then the video goes into this whole thing about electromagnetism.
Ah, yes. Things are about to get really interesting.
Lay it on me.
So at the time, people were studying electricity and magnetism
Okay.
and how these forces could act at a distance.
Right, like magnets, they don't have to touch to push or pull on each other?
Exactly. And so to explain this, they came up with the idea of fields.
Fields?
Yeah, basically these invisible zones of influence that surround charges and magnets.
So instead of things like magically affecting each other from far away,
There's this field that connects them.
that's a cool way to think about it.
It is. And then along comes this brilliant physicist, James Clerk Maxwell.
I've heard of him.
Oh, he's a legend. He unified the laws of electricity and magnetism into these beautiful equations.
Okay.
And get this, his equations show that disturbances in these fields travel at a very specific speed.
Let me guess the speed of light.
You got it.
Whoa, so light isn't just any wave, it's a wave traveling through the electromagnetic field.
You nailed it. That's the big reveal.
That's pretty mind-blowing.
It is, but hold on tight because the story doesn't end there.
Oh boy, I have a feeling things are about to get even weirder.
You have no idea we're about to enter the quantum realm.
Quantum mechanics, this is where things start to get really trippy, right?
You said it, and one of the biggest surprises of quantum mechanics
Yeah.
is that light can also behave like a particle.
Wait a minute, I thought we just established that it's a wave.
It is, but it's also a particle. It's what we call wave-particle duality.
How can something be both a wave and a particle?
It's one of the biggest mysteries in physics, but experiments show that when you dim light down to extremely low intensities,
Okay.
it hits detectors like little individual raindrops rather than a continuous stream.
Raindrops instead of a stream, so it's like it comes in these tiny packets.
Exactly, and each one of those packets is called a photon, a particle of light.
So light is like this wave-particle hybrid. I'm trying to wrap my head around this.
It's not easy, but the video does a good job of explaining it. They talk about this concept called superposition.
Superposition, that sounds familiar.
It's the idea that a quantum particle, like a photon, can exist in multiple states at the same time.
So it's not just that we don't know which state it's in actually in all of them at once.
Exactly. Until we try to measure it, then it collapses into a definite state.
Wow, that's messing with my head.
It's definitely counterintuitive, but that's the beauty of quantum mechanics.
So by studying light, we're not just learning about photons and waves, we're actually probing the fundamental nature of reality.
Light is our window into this strange and wonderful quantum world.
This is incredible. We've gone from simple particles to waves to this whole quantum craziness.
And we're just getting started. There's so much more to explore.
Okay, well, I am hooked.
I call.
I can't wait to see what other surprises light has in store for us.
You're in for a treat.
Well, on that note, let's take a quick break and we'll be back to dive even deeper into the mysteries of light. All right, so we're back and ready to tackle the next layer of the light mystery.
You ready for some more quantum weirdness?
Hit me with it.
Okay, so remember how in part one we were talking about how light can act like both a wave and a particle?
Yeah, wave-particle duality. My mind is still blown.
It's pretty wild, right? But it gets even weirder.
Okay, I'm listening.
So there's this thing called the Hanbury Brown and Twiss effect.
Hanbury Brown and Twiss, that sounds like a detective duo.
Haha, right out of a 1950s film noir.
So what did these physics detectives uncover?
They basically showed that photons can be kind of clingy.
Clingy photons. Now I'm really intrigued. Tell me more.
Okay, so picture this. You have a light source emitting photons.
Got it.
And you split the beam in two, sending each half to a separate detector.
So we're basically eavesdropping on these photons to see what they're up to.
Exactly. Now, logically, you'd think the photons would hit the detectors randomly. Like if you were flipping two coins, the result of one flip shouldn't affect the other, right?
Yeah, that makes sense.
But that's not what Hanbury Brown and Twiss found.
Really? So what happened?
They noticed that when the detectors were the same distance from the light source, the photons tended to arrive at the detectors at the same time way more often than you'd expect by pure chance.
Wait a minute. You're telling me that even though they're emitted randomly, they somehow know to arrive together?
It's like they have this secret pact to show up at the party as a pair.
That's wild. How is that even possible?
It all boils down to this quantum property of photons called indistinguishability.
Indistinguishability.
Yeah, basically it means that photons aren't just similar, they're completely identical. You literally cannot tell them apart.
Like identical twins that even their own mother can't distinguish.
Exactly. And this indistinguishability has huge consequences for how photons behave.
Okay, I'm following so far. So how does this explain the whole synchronized arrival thing?
So in classical physics, we calculate the probability of two events happening by multiplying the individual probabilities.
Right, like the chances of rolling a 6 on 2 dice.
Exactly. But because photons are indistinguishable, we have to approach it differently. It's like they're not separate entities anymore. We have to consider all the possible ways they can reach the detectors together.
So because they're identical, there are more ways for them to end up at the same place at the same time?
You got it. In the quantum world, indistinguishability creates this kind of interference pattern. And for photons, this interference increases the likelihood of them arriving together.
Yeah.
It's what we call photon bunching.
Photon bunching. So even though they start out random, they end up synchronized just because we can't tell them apart.
Exactly. It's like they're saying, hey, if no one can tell us apart, let's just stick together.
Quantum mechanics is so bizarre.
It definitely keeps us on our toes.
Yeah.
But this bunching behavior isn't just a weird quirk. It's actually what makes lasers work.
Lasers? I thought lasers were all about amplifying light. What does that have to do with photons being clingy?
Well, amplification is part of it, but the real magic happens in how lasers generate light in the first place.
Okay, how do they do that?
So inside a laser, you have excited atoms that release photons, right?
Right, just like any other light source.
But here's the twist in the laser. The emitted photon doesn't just fly off on its own. It can interact with other excited atoms and cause them to release identical photons.
So one photon triggers a chain reaction of clones.
Exactly. It's like a photon flash mob. And guess what drives this chain reaction?
Yeah.
You guessed it, indistinguishability. Because the photons are identical. They bunch together, creating that super concentrated beam of light that we call a laser.
So a laser is basically just the Hanbury Brown and Twiss effect on steroids.
You could say that it's quantum weirdness playing out on a macroscopic scale.
This is blowing my mind, but I have a feeling we're not done yet. The video ends with this cliffhanger about photon anti-bunching.
Ah, yes.
Yeah.
Things are about to take another turn.
So what is anti-bunching? It sounds like the opposite of bunching.
You're exactly right. With anti-bunching, we can actually manipulate photons so they arrive at detectors separately, one at a time.
Wait, you're telling me we can make photons act like they're avoiding each other?
It sounds crazy, but that's the power of quantum optics. We can actually control the states of photons and create these exotic states of light that completely defy our classical intuition.
So it's like we're playing quantum billiards using lasers and mirrors to make photons dance to our tune.
You're getting it. And these quantum optics experiments aren't just for fun. They have the potential to revolutionize everything from microscopy to computing.
Okay, I'm officially hooked. Let's dive into that in part 3 where we can unpack the bigger picture of what it all means. Okay, so we've gone from Newton's particles to Maxwell's waves.
We've tangled with superposition and indistinguishable photons.
It's been a wild ride.
It has.
So now I think it's time to step back and ask the big question.
What's that?
What does all this quantum craziness tell us about the nature of light?
And maybe even reality itself.
Right, exactly.
Yeah.
I mean, it seems like light is kind of a portal into this really strange world.
It really is. Our brains are wired to see the world in this classical way.
Yeah, things have definite position.
They move in predictable paths.
Cause and effect?
Right, but then quantum mechanics comes along and says, nope, not so fast.
It's like we've been living in this simplified version of reality.
And quantum mechanics is the red pill that shows us how deep the rabbit hole really goes.
So by studying light, we're not just learning about photons and waves.
We're actually getting a glimpse of the underlying fabric of the universe.
And that's pretty mind-blowing.
It is, and it has some pretty big implications, not just for our understanding of the cosmos, but also for technology.
Oh, yeah, you mentioned that in part 2.
Right, the whole thing about photon antibunching.
Remind me again. How does that work?
So with antibunching, we can manipulate photons so that they arrive at detectors separately, one at a time.
It's like they're deliberately avoiding each other.
Exactly. It's a phenomenon that you just can't explain with classical physics.
So what can you do with these antisocial photons?
Well, for one thing, you can use them to build incredibly precise microscopes.
Really, how?
Because the photons arrive one by one. You eliminate all this background noise and interference.
So you get a much clearer picture.
Exactly. You can see details that would be completely invisible with traditional microscopes.
It's like having a quantum scalpel that can dissect light itself.
I like that analogy, and the applications go way beyond microscopy.
Like what?
Well, for example, scientists are exploring ways to use antibunching for secure quantum communication.
Quantum communication, that sounds like something straight out of Star Trek.
It kind of is. The idea is that you can encode information onto individual photons.
And because of the whole anti-bunching thing?
Any attempt to intercept those photons would disrupt the signal.
So you'd immediately know if someone was trying to eavesdrop.
Exactly. It's like having a built-in alarm system for your messages.
That's incredible. What else can you do with this quantum trickery?
Well, one of the most exciting areas is quantum computing.
Quantum computing, that's the thing where computers use the strangeness of quantum mechanics to do these crazy calculations, right?
Yeah. And photons are actually ideal for building the building blocks of quantum computers.
Which are?
Quantum bits or qubits.
Qubits. So instead of ones and zeros, you have these quantum bits that can be both 1 and 0 at the same time.
Exactly. And that opens up a whole new world of computational possibilities.
It's like our computers suddenly got a massive upgrade.
That's a good way to put it. Quantum computers could revolutionize fields like medicine materials, science, artificial intelligence.
It sounds like we're on the verge of a technological revolution.
We very well might be. And it all goes back to this fundamental question of what is light?
Wow. It's amazing to think that something as simple as light could hold the key to unlocking such incredible possibilities.
It's a testament to the power of scientific curiosity.
This deep dive has been an incredible journey.
It has.
You've really helped me see light in a whole new way.
It's not just something that illuminates the world.
It's a fundamental ingredient in the cosmic recipe.
It's a window into the quantum realm.
And who knows what other amazing discoveries are waiting out there?
That's the beauty of science. There's always more to explore.
On that note, we'll leave you to ponder the mysteries of the universe and the incredible story of light.
Until next time, keep those curiosity lights burning.
And remember, stay curious.